things go from metaphysics to physics the moment that you are talking about falsifiable things. And that's fantastic.
Eduardo Martin-Martinez, thanks for being here.
A pleasure.
It is commonly accepted, and I quote from a recent paper of yours, that at the Planck scale, no experimentally verified theory provides a framework for measuring space or time. At these scales, the theory of general relativity can be argued not to be valid anymore, since there is no notion of ruler or clock. What are these rulers and clocks you talk about, and what's the problem with short scales?
All right, so maybe to give a little bit of context, right, and the theory of relativity and general relativity, as in particular what we're talking about, it's should be able to be formulated, and indeed can be formulated, out of just talking about local observers, and local observers are observers that carry a clock, have a notion of proper time, and carry a small ruler, have a notion of, if you wanted, local length, if we want to say it like that. So the general relativity is a classical theory and does rely on those notions of being able to have clocks and being able to have rulers. Now the problem, if we approach it from the operational point of view, I mean, of course, mathematically you can develop the theory just based on those local notions of clock and ruler. The problem is that at some point, when we're trying to model these clocks and rulers at a scale that is, if you want, microscopic enough, or in other words, which is equivalent to say that for energy that is large enough, those clocks and rulers don't really correspond to anything that we see in nature. We don't have any natural system that we look at, oh, this is our clock and this is our ruler. That is classical, that has these notions of measuring distance, if you want, or measuring time intervals, the same way that the clocks and rulers that we have and we build start to be quantum systems. And it starts to be a little bit difficult to talk about classical notion, if we want, of what is a measure of time and what is a measure of distance. No, so in the context that quote is provided, so one. That article in particular tries to deal with, okay, what if we redefine the notions of ruler and clock as quantum systems? We actually use quantum systems to substitute the rulers and clocks and try to build something like general relativity, but in the basis is using a quantum notion of clock and a quantum notion of ruler, if we want. And the framework to do that that we follow in that paper is something called quantum field theory, together with the theory of measurements in quantum field theory, which is extremely interesting in itself, because already in quantum mechanics, making measurements is a very complicated topic and a very open to discussion. What does it mean to measure a quantum system, and what happens with a quantum system when you measure it? Quantum field theory is, in a way, a relativistic formulation, a formulation of quantum mechanics that's compatible with relativity. Often said that it can, I mean, in popular science, you often hear, you can definitely do relativity and quantum mechanics in a consistent way. That is quantum field theory, and quantum field theory in curved spacetimes. Now, that doesn't explain the dynamics of gravity, completely different story, but it gives you a framework in which you can actually handle both. And then within that framework, rebuild the framework based on it on something that is operational measurements, like, for example, using atomic probes or something similar to atomic probes to probe quantum fields and give a notion of clocks and rulers. So very roughly, that is what that research is, this piece of research that you mentioned is about.
If I may summarize what you said, in a way, general relativity is a classical theory, meaning not a quantum theory, in which
That's
we
right.
employ some classical notion of clock and ruler, which has no mystery behind it, just clocks and rulers, physical systems to measure time and lengths in a way. But when you go to short scales, where the word gets quantum mechanical, you need a quantum mechanical notion of ruler and a quantum mechanical notion of clock. Is that correct?
That is exactly right, yeah.
Perfect. And this has to do with measuring space-time. You brought up
That's right.
measurements in a more general setting. So before going into the details of quantum mechanics and the ways in which it can be a bit weird for a classical being as me or you. Can you please expand a bit on this difference between measuring stuff in quantum mechanics and measuring it in quantum field theory?
Yes, so this is a great question actually, because there are, and if I may, I can talk about three levels of measuring. Right? One is when we measure in classical systems, second level when we measure quantum systems, what it means, and a third level is when we measure quantum systems in a way that we need it to be compatible with the structure of spacetime, with relativity in this case, because those are three different levels of complication that makes it less and less trivial to make measurements. So the idea of measurement is, I think, is very easy to relate to everyday life in classical systems. We assume that there are some quantities, dynamical functions, as we say more technically, some quantities that can be measured. And what does it mean to be measured? Well, there's an experiment, there's some protocol that maps the state of a system, let's say in this case a classical system, to a number. And that number is something that you can write down in a piece of paper. An experimentalist could write it down on a notepad. An example of that is, imagine that I want to know what is the value of the electric field in my room during the time of this interview. So you set some region, right, in space and time if you want, and I want to talk about a physical system, in this case the electric field, and I want to measure the intensity of the field. And then I make a measurement, and that measurement, I have some machine that reads out the electric field intensity. Perhaps it's an antenna, perhaps it's simply a charged object that will move attached to a spring that will move depending on the field. And that gives me a value depending on the force, and I see the displacement of the charge. I get a value and say it's like 42 volts per meter, for example. Then I can write down that on a piece of paper. This is what we mean by measurements in classical systems. We have some physical system that is in some states, and we want a map that is modeling. It's giving me the model that goes in the theory in which I explain the system, gives me the model that translates the dynamical state of the object to a number that I can understand, or a sequence of numbers, right? A number, maybe a number and uncertainty, some experimental protocol. And what we call measurement theory in this case, the measurement theory of the system, is precisely how we mathematically model the transition of going, well, I had the physical system, I do an experimental process, and that experimental process spits out a number. Classically, I don't think that's very problematic, because we're very used to classical systems we even think as the value of measurements as, in a way, as being intrinsic, as being the property of the system, meaning like that car has some speed, I can measure it with a speed gun, and it's a property of the car moving right there. Now, things get a bit complicated when we talk about quantum mechanics. And they get complicated in a very weird way, because in particular, we know that in quantum mechanics, we can prepare acceptable physical states for which the outcome of a measurement is not deterministic. So we can have the superposition. I mean, for somebody who knows quantum mechanics, we can have two eigenstates associated with two different eigenvalues of the velocity of an object. Or if you want, like a Schrödinger cat, you can have a superposition of a car going at velocity 3 meters per second and velocity 1 meters per second, and we can create that superposition, not with a car typically, but we can create it with smaller particles. And we want to measure the velocity, the speed of that object. Now, we know that when we measure the speed of that object, we can do the experiment. The typical experiment that we think of this in introductory quantum mechanics is something called the Stenger-Lach experiment, where you have a magnetic field oriented in some direction, and you have electrons coming in with different spin, and depending on the spin they have, they will be deflected in one direction or another. And you can create superpositions of the state of the spin of those electrons in that direction be a superposition of up and down in those directions, meaning that they don't have a definite value a priori of the spin in that direction, rather they're a quantum superposition of two values. And when we do the experiment, we don't observe anything particularly weird, in the sense that we don't observe the two things happening simultaneously when we do the experiment. We observe either the electron deflects up or deflects down. We see either one or the other. So we measure, if we were talking about the car that I said before, we would measure either velocity 3 or velocity 1 or velocity, or whatever other velocity is included in that superposition, but we would not see all of them at the same time at every instance we do the experiment. We would actually see a particular value. That is the typical analogy with the Schrödinger cat. No, if you look into the box, the cat is either dead or alive. So something happens. So the experimentalist definitely writes down a number when measures the speed, or the electric field, 42. Now, the interesting thing in quantum mechanics is that if I do a sequence of measurements, is right after measuring the speed of the car, I measure it again, the result that I get is the same as I got before. Suddenly I went from, I don't know a priori what the result of the measurement will be. It could be one of several options, like a Schrödinger cat, right? The Schrödinger cat, I don't know a priori if the cat is dead or alive when I measure, but if I check and it's alive, and I close and check again, it's going to be alive. And that is interesting. We went from a non-deterministic outcome of an experiment, meaning like we cannot predict a priori what the outcome will be, to now I can. Once I have the information that a measurement provides, now it becomes deterministic again. The outcome of the experiment is going to be the same. It has to be, is the compatibility of sequential experiments. And that is what led to many things that in the past were thought as even today, some of the things get in the realm of interpretation of quantum mechanics. But in the times of the Copenhagen discussions, people start talking about the notion of collapse of the wave function. The collapse of the wave function saying the moment when we measure, we have changed the state of the system. And by changing the state of the system, now the system is in a different state in which we know exactly what the outcome of an experiment will be. This is, even without talking relativity, this is already kind of, how to put it, controversial, if we want, because this is a very weird thing that no matter how I measure, I am acting on the system. And then when we talk later on, I think we will talk a bit about entanglement, things becomes even weirder when you consider this collapse. But this notion of collapse, in a way, requires that you are instantaneously updating the system. And that notion of collapse, in a way, it's incompatible with quantum mechanics itself. And let me talk about it. It's because quantum mechanics, it's like for the notion of collapse, you need to divide the world into two different categories. Things for which quantum mechanics work and measurement apparatuses. And measurement apparatuses are weird objects. Measurement apparatuses are actually very weird because are things that what they do is they collapse the objects that they interact with. And this collapse, we know, cannot really come from the same fundamental interactions that we model, because those collapses, at least in some cases, are not going to be able to be explained through unitary interactions, what we call unitary dynamics, so Hamiltonians, for people who know about this, interactions in the same way that quantum systems interact with each other. We need something else for that. And that makes it problematic within quantum mechanics. Oh, sorry, Davide.
In a way,
Yeah.
if I may jump in, just to summarize, within quantum mechanics, you have this collapse phenomenon, which somehow would imply you'd first of all have an instantaneous update of the system, as you said, which does not violate special relativity, there's no communication, but still there's some notion of simultaneity within the theory, which seems to be a bit weird. And you'd have this problem of the Heisenberg cut, as someone would call it, right? You should distinguish between systems and measurement apparatus, and this is a bit weird for a fundamental theory. Some philosophers of physics would say fundamental theory should not include objects like macroscopic objects, measurement apparata like cats or pianos. I think Tim Maudlin once said that, like, you should have no pianos in your fundamental theory, while a measurement apparatus seems not to be a fundamental object. It really seems to be like composed of particles as any other physical system. Is this what you've said?
Yeah, so in the usual notion of collapse of the wave function, the measurement apparatus is not emergent from the theory of the microscopic theory. We say somehow, I mean, physicists, to feel good with ourselves, we often say, well, those are macroscopic objects, right? Of course, they will be internally quantum mechanical. It's just very complicated. But we cannot. In fact, we have theorems that tell us that you will never end up with something like that in all possible cases. if you really want to recover what measurement apparatus you claim they're doing, right? They don't emerge. And it's right. Philosophers of physics wonder then if quantum mechanics, with this notion of collapse, right, is a fundamental theory or not, because you cannot have the reductionism of the measurement apparatus to microscopic objects that are explained within the theory. So indeed, that is a bit problematic. I will mention again the compatibility or not with relativity at the third layer, I think, if that's okay.
Perfect. Absolutely. Yes. Yes.
And maybe before that we should talk about entanglement. But just to close the quantum mechanical one, right? I think we can all agree uncontroversially that the notion of collapse is not devoid of problems. The notion of collapse, while you need something like you need a state update to explain the world. Without state update in quantum mechanics, we are not able to explain experiments. And it works, let me say, for many experimental regimes that we use. As an effective model, it works fantastically. You can do crazy things, and you can do quantum erasers, delayed quantum erasers, you can do crazy experiments, and mathematically you can model things with collapse, and they seem to work well, at least in those regimes, let me emphasize that. Yet they're very problematic fundamentally, so, or at least not uncontroversial in that sense. And now let me just say, to end this before we talk about entanglement, that when we go to the third level, when we want to have a fully relativistic quantum theory, like quantum field theory would be, and we want to talk about measurements within QFT or quantum field theory, things are even worse because, and I will just preface it, if you impose the same, if you try to do the same notions of collapse in QFT, you can actually violate relativity. You can have things that are not compatible with the axioms of the theory in QFT. And I will give more details about that maybe after we talk about entanglement, because it allows us to, entanglement I think will allow us to put in context what the problems could be in a way that I think more understandable than just talk about the technical
So
part.
you've called for it. I guess it's time to talk about entanglement and make it clear, because there's a lot of misconceptions, going around. We are on YouTube, so there's a lot of people on YouTube talking about entanglement. I guess it would be better for us to make entanglement clear now and then move to quantum field theory, as you said. So feel free to start and make it clear for us.
Sounds good. All right, so maybe I can start by saying what entanglement is not, that it's often portrayed
Yeah,
as.
sure.
And then
That's to remove all misconceptions before introducing proper conceptions.
yes, and then we talk about it. So in popular science, I don't think, definitely not as common among people who are more interested in physics, no, but in popular science it's often, and in movies, popular culture is often portrayed somehow with this weirdness of, well, I measure something, I have an entangled pair, two systems that are entangled. I measure the first one, and then people say, well, automatically there is a change on the other system, that the other system feels it, and then information in a way is transmitted by the action on the first system to the second. That's certainly not the case. And in fact, I would argue that the fact that I measure A, let's say we have two systems A and B, the fact that I measure A and then B, once I measure A, say that you have two entangled Schrödinger cats to make it concrete. In two entangled Schrödinger cats, say that they are in a superposition of two cats being alive and two cats being not alive. And that is in an entangled state. And then Alice measures the cat, and Alice finds out that the cat is alive. It is true that Bob will find, if Bob measures in the future, Bob will find the cat being alive, never dead. Whereas Alice could have found either, Bob will not. But let me just give, this is certainly also not what is intrinsically defining entanglement, because that's what defines correlations. And let me give you I always give you an example that to debunk this mystical idea of, oh, Alice A and then finds out B. I can have a black ball and a white ball, only these two balls, and I put them in a bag. Nothing quantum about them, just a white and a black ball. And I can ask, say that I'm Bob, and I can ask Alice, pick one, but don't show me. Don't even look at it yourself. Don't show me. Alice picks one, and then Alice goes far away. Say Alice goes to Alpha Centauri. And then I say, okay, I don't know what the color of the ball of Alice is. In fact, if in physics we are forced to describe mathematically the color of the ball that Alice has, we would say, well, it's a probabilistic distribution, 50-50, being black or white. We don't know any better. In this case, even if the ball has a color, we don't know any better. Our best description is to say 50% white, 50% black. So, I don't know. But what could happen is that I can actually measure my ball. I can look at it, look at the color, say it's white, and I say, Alice, your ball is gonna be black. And then Alice measures and finds it black. I don't think many people will be very impressed with my ability to guess the color, because we knew that in the bag we had a black and a white ball to begin with. So we had correlations between the colors. So I could even get mystical and say, oh no, by measuring my ball, now I know that Alice will always have black. Yeah, no, that is definitely not the case. And this is just due to the fact that we had correlations to begin with. Now, it's a little bit more difficult to conceptualize in the case of quantum systems, because the difference here is like having two systems that the outcome, so in this case, there was a value for the color already defined. It's just I was ignorant about it. And I have a notion of ignorance about it. Because I'm ignorant about it, I am forced to describe it with a probability distribution. In quantum mechanics, you are forced to describe systems with probability distribution, not only because you may be ignorant about it, it's because they fundamentally are in a state that force you to describe it with a probability distribution. Now, an example that is different from this is like, well, you can have two dice in an entangled state, so that, go ahead.
Yeah, pardon me, if I may jump in for a second.
Please.
So what you're saying is that in the previous thought experiment, the one with the black and the white ball, all the probabilities regard us being ignorant about the ball's colors, right? Regardless of Bob measuring or not his ball, Alice's ball will always have that specific color, which can be either black or white, nothing to do with what Bob does. As soon as Alice leaves the house with the ball, the color is either white or black, and it will be white or black forever, right? That's the case. While quantum mechanics seems to be a bit different, so please take all the time you need to explain.
A bit different, but I'm going to argue that not in the way that sometimes is thought about. So a bit different in the sense that it's now having like the two systems, instead of being a ball that has a defined color to begin with, consider a die. Die that can give you, you throw it, so when you measure it, you throw it, it can give you anything from 1 to 6, say. And we prepare that die in an entangled state with another die that Alice takes. And the state is such that I know when Bob rolls the die and gets a 3, Alice will also get a 3. So what is interesting here, though, is that a priori, neither Alice nor Bob have a defined outcome of the measurement. There's random, it's locally random. However, what makes the entanglement, the property of entangled state here interesting is that we know that no matter who measures first, no matter when they measure, we know that the measurement will be the same. And I think that is actually a very important distinction, because it's not that Alice rolls the die and because he measures a 3, she acts at a distance on Bob's state. I would never say that. I would say instead, no. It's because the die were correlated, and the correlations go in the following way. No matter what the outcome of the measurement of Alice is, no matter what it is, we know that in the end it's going to be correlated with the outcome of Bob, even if a priori the outcomes are random. And I think this is really important, and a distinction between the action at a distance paradigm, right? Einstein, Podolsky, and Rosen were very bothered by that, and for good reason. In that sense, they would be right. This is very problematic in many ways. And above all, for example, if we consider that in relativity, as you mentioned, there's no notion of simultaneity. So if the measurement events, right, between Alice and Bob are what we call space-like separated, so say that Alice is in Alpha Centauri, I'm here, and the measurements happen in an interval of an hour with each other according to my clock, so they are space-like separated, we know that I can have 3 different observers that are all valid observers that would disagree strongly on who measured first, We have a person that would say a person that is co-moving with me, my neighbor that's sitting here would say, no, you measure first, and then later on, Bob measures. So you collapse the wave function, and then because of that, Bob measures something else. Then somebody else also here, but is traveling with some relative speed with respect to me, may say actually no, the thing from Bob actually happened first. So Bob measured first, and Bob collapsed the wave function to you. This notion of action at a distance is incompatible with the notion of relativistic simultaneity. The fact that different observers, for events that are space-like separated, that is farther away, happen in time in an interval that is shorter than the time would take for light to move from one side to another, you cannot talk about this notion of collapse in an objective way. If you want a collapse model, you're going to have to be contrived enough to say that it's observer dependent. And this is the kind of ways of building a theory that physicists start to say, this is too contrived.
Epicycles, right?
Go ahead.
It's like epicycles in...
Yes. And as a summary, I would say that it's a bad idea to think about entanglement in terms of it's a state, so that is this notion of often no use of non-locality. When I act here, I have a non-local effect over there. I don't like it. It's very bad. It induces confusion. Much better to think about it. It's a kind of correlations. Similar to the classical balls and the colors, only they are quantum. They cannot exist within the quantum framework, but they do exist within the classical framework, but they do exist in the quantum framework. And there's correlations, the same way they were correlations in the past, just slightly different. They could be correlations between the outcome of measurements of things that are not determined to begin with, but no matter what the outcome will be, it will be correlated with the other person. So the one thing, I guess, maybe I can let you maybe clarify. You're really good at clarifying the things that I say, but I can also add how I would actually define entanglement then, after having talked a lot about what is not, in my opinion.
Yeah, I think this is a good point for us to get into an actual definition of entanglement, because you kind of propose these two thought experiments that make the difference, I would say, clear, because in one hand we have properties being defined and then discovered later, but there's nothing mysterious about that. It's the usual, if I may, socks thing, right? You take the right socks, and as soon as you see that's the right socks, you know the left socks is too. Like, sometimes people describe entanglement in those terms, but that's not correct either, right? It's too demystifying, right? You either mystify too much or demystify too much. While in the Alice and Bob quantum experiment, you actually have intrinsically probabilistic phenomena which are nonetheless correlated with one another. And if you're happy with that, we can move on with your definition of entanglement.
Definitely. So the way I'd like to define entanglement, and I'm a very foundation of quantum info inspired person for this, is the following. Now, let me just first give a definition and I'll clarify with an example. Entanglement is the extra ignorance about a system B that you gain when you erase information about another system A. And that would be, to me, the most conceptually accurate definition of entanglement. And let me put it, we can talk about what it means mathematically, and we can talk about non-separability and so on, but conceptually, let me put it like this. If I have two classical systems, correlated or not, well, let's say two classical systems, say I have two books, and they could be correlated, right? I can read, could be correlated, they could be the same author. One could be, a spin-off of the same thing. I can read book A, and I don't need to read book B, and I can, by reading book A, I get all the information that I can get about book A. If suddenly I have the two books and I read the two books, but somebody erased from me the information about one of them, I don't lose the information about the first book. So if I read, let me put it like that, I don't know, if I am reading a biography of Einstein, and I'm reading a biography of Feynman, and somehow somebody erased from my memory the biography of Feynman, I don't lose the information about the life of Einstein, still there. This happens in the classical world. That is it. You don't have the case that by erasing information about a subsystem, something else that is not the system you're considering, you lose information about the system. Now, in the quantum world, you could have a system of two subsystems that are correlated, so that when I erase information, when I have both, I have full information. In this case, would be I have the life of Einstein and the life of Feynman. I have full information about both. But so that when I erase information about the first one, suddenly the other one becomes gibberish. I have no idea. It contains no information. So this notion of having a system composed of two subsystems, for which I know everything about both, or I know as much as I can know about both, but I erase one of them, and I'm left with more ignorance after doing that. This is, to me, what is at the core of entanglement. This amount of lost information because I erased information about something else. Yeah.
So could we say, and tell me if this is stretching it a bit too much, that in quantum mechanics, information is more distributed than in classical mechanics, and entanglement somehow measures that? Do you agree with this?
No. Yes, I think in a way, yes. So in a way, to know about the subsystems is not enough to know the individual subsystems. You would be still ignorant if you get all the information you can get about subsystem A, only subsystem A, plus all the information you can get about subsystem B is not enough to describe the system of both of them. And that doesn't happen classically. Classically, if I have the information about all the parts of the system, I have information about the full system. Whereas in quantum mechanics, you can have cases where it is not enough to describe the parts individually in order to know the information about the total system. And that manifests, like for people who are more into it mathematically, in something called the notion of non-separability, which is the inability of describing my system of, let's say, two subsystems as some classical probability distribution of correlated pairs, classically correlated pairs in a way. So that is, if you cannot do that, you're going to have entanglement. Yeah.
That's extremely interesting. So somehow when you go to quantum mechanics, you take classical probability and you add something more, which is precisely entanglement, which connects subsystems more than in classical settings. Okay, this is weird, but I guess we're fine with it. What happens when you go to quantum field theory? What happens when you, because you said that you have this, let me call it tension with the absence of simultaneity, because it's not really a paradox in the sense that we know that you cannot really send information with that. So somehow we save the no signals going faster than light, but still you have some kind of tension with this. You know, it doesn't sound intuitive, or it doesn't sound to work at a conceptual level. So what happens when you go to quantum field theory?
So yes, this is very interesting. So as you say, traditionally we do in quantum mechanics, and we don't care about QFT, and we do in quantum mechanics, we say, well, we know that there's no operational protocol in which I can actually transmit information only with entanglement. You're going to have to at least signal something. You have to send information, and that information has to be transmitted by some classical channel. And that information that is transmitted through some classical channel, it could be a quantum channel, but has to be transmitted materially from point A to B. That is limited by the speed of light. And then we're happy with imposing this restriction, because you need that bit of communication. You are restricted by the speed at which information can propagate. Otherwise, on its own, entanglement is not enough to transmit information, and then you're fine with that. This is not satisfactory for people who care about foundation of QFT, because in QFT, we don't, let's say, don't impose on what we know some relativistic conceptions. We actually build them from the bottom up. What we do in QFT is we axiomatize the same way as the postulates of quantum mechanics are important. At the same level, the postulates of relativity are baked into the theory as well. So there's several postulates. It becomes pretty abstract and complicated. But let's say that the postulate of microcausality, which is again the same thing, that there is no ability to figure out about an observable. Now you have physical systems that are quantum fields that are relativistic. Think of the electromagnetic field itself. Electromagnetic field can be, and it's quantum, and we know it's very quantum in many regimes. So now we talk about the field amplitude in some room, in some laboratory in Australia, and the field amplitude in here. We bake into the actions of the theory that it's not possible to measure, to figure out the amplitude of the field here, just measuring locally the amplitude in Australia. we actually impose that as an axiom, that operationally, the operations that are physical cannot alter non-locally. You see, that's why, and then if you want, we can just later on talk about this, because I definitely would love to clarify when people talk about quantum non-locality. This bothers a lot people doing QFT, because to me it's not that. It should be quantum non-local realism. And we can talk about it if we want, because the non-locality part is not what feels to me, it's the realism part what feels to me. But in any case, the point being that it's baked into the theory. Now, that is super interesting, and things that are extremely interesting happen. Like, for example, the ground state of the ground state of the electromagnetic field has entanglement everywhere, which is crazy. There's a lot of entanglement in the field. In the ground state, you go to absolute zero, and in absolute zero, what should be empty, we call it a vacuum, as empty as it gets. It's actually a lot, if you want to talk popular science-wise, would be correlated fluctuations if you look very, very with a magnifying glass, and there's entanglement contained between the things that are space-like separated. But the theory, and it's funny because that's a consequence of the theory actually being relativistic. The fact that you cannot signal from A to B baked into it, instead of imposed like we do in non-relativistic quantum mechanics, baked in from the beginning. One of the consequences is that entanglement is everywhere, which may be counterintuitive, but it's what you have, and it's crazy. But that makes things complicated. The fact that imposing relativity as an axiom in the purest way, let me put it like that, this is the less contrived way of doing it, not by saying, now it comes from outside to impose it. No, let's build the theory already taking into account this. We have entanglement everywhere. Now, one of the issues that we have is that if we try to copy what we do in non-relativistic quantum mechanics and say, let's work with measurement apparatus, right, that perform projective measurements, is what we call those idealized measurements that give you a value, right? Let's say that I measure the field and I have a 42. If I try to build the equivalent, like the projector that acting on the field updates the state so that the amplitude is 42 after the measurement, you can prove very easily that I can build a protocol that, if that operation was allowed, I could build a protocol that can transmit signals faster than light. And that is related, for people who are interested, I won't say much about it because it's a complicated thing to talk about in a video, I think, but it's related to the fact that the algebras of observables of the field are what they call type 3 von Neumann algebras. So they're weird, they don't admit, you don't have any projectors in the algebras of observables that are allowed and are compatible with relativity. And because you don't have to, you're taking, to make a projection, you're taking an object that is not from the theory and that ruins one of the postulates of the theory. And that's called the measurement problem in QFT, and what discovered in the 90s, first pointed out by Raphael Sorkin. And it was very devastating, because that means that the theory that we believe is fundamental, the standard model, the best theories that we have to explain what we can see, use quantum field theory, and is the theory that has made the best predictions to experiments so far, like matching 14 digits of precision of what experiments would find. And yet, we don't really have a valid measurement theory. If you try to shoehorn the one that you use in quantum mechanics into QFT, you destroy the theory. You blow the axioms of QFT.
Just to tell our audience how extreme this is, let me please stress that when you do physics, you start from observing the world. You start from measuring what happens around you. And then you start constructing your classical physics, your electromagnetism, then you discover you need relativity and quantum mechanics, then you somehow put together quantum mechanics and special relativity, starting from your observations, like the standard history of science 101 starts with people, observing the world and then trying to make sense of it. And you end up with an extremely precise, accurate, successful model of the microscopic world, which should be our fundamental theory, in which measurements do not work.
That's right.
Somehow you lose your starting point.
Yeah. And that's why I believe that it's extremely important to take a step back and develop a measurement theory for QFT. It's one of the things that I do, not only me, and there are several people, different groups working on precisely this. Like, what does it mean? I know you have a working model that may explain some experiments, but we know it's fundamentally unsound and in some extreme regimes, it's going to fail completely. And so we need to take a step back and actually develop a proper measurement theory for QFT. We cannot go back all the way to Copenhagen in the 20s and in the 30s and use what they told us to do. Now it's not just that it's uncomfortable, as we discussed before, saying that there's measurements apparatus that are separated from quantum systems. Now it's worse. It's like, no, it's not compatible with the theory to do the same thing as we did before. We could, if we introduce those extraneous objects, we break the theory in a way that would allow you to do, I don't want to say it on YouTube, but would allow you to do horrible things. You can do horrible things. If those things are allowed, your theory is no longer lose the predicting power that the theory has. Yeah.
Sure. But within this context, can you please add something on the non-locality problem you mentioned before?
Right.
Like before bringing rulers and clocks into the equation and our discussion, making things much more complicated. Can you specify a bit why you find this non-locality ambiguous in the way which is usually discussed?
Certainly. As a summary of what I want to talk about with this is two things, right? One is, what does locality mean for a field theorist and for a relativist, if you want? And what does entanglement mean with the notion of locality? What is relation? And talk about the Bell experiment and so on. So in the notion of locality for somebody working in relativity, or in general in a field theory on causal structures, the notion of locality, it's related to the fact that, well, if we conceptualize the notion of event, which is some experiment, if you want, that happens somewhere at some time, that's the notion of events, right? This conversation would be an event, for example. So there is the relationship between events is not arbitrary. There's something that we call a causal structure, meaning there are events, right, that can be influencing other events. For example, this conversation may be influencing how I feel in an hour, but it cannot be influencing what I did yesterday. So there's this notion, this very empirical notion, that there's some causal structure. Now, the notion of locality relates to this. When I do an operation here, I cannot be affecting something that is very far away. There's some, as we say, some causal relationships. What I do here can be only cause of some other things, not all of them. What I do here right now cannot be affecting Australia at the same time. At the very least, I can only affect Australia after enough time for light to go from here to Australia. That's the relativistic notion of causality, if we want, or locality, which we use it actually. Locality and causality they're very strongly related in relativity, right? Now, that notion of locality in the abstract sense and in quantum mechanics is the notion that we have two labs that we assume that experiments that we do in lab A can be independent of the experiments that I do in lab B. For example, and the typical example that we use in the Bell experiment that I would say here, the notion of locality is that the knobs that decide the decision about how am I going to orient my experiment, the knobs and the settings of my experiment are decided by me and my collaborators, but whatever they do in Australia, they cannot change them. That's the idea of locality. There are independent labs that can make their own decisions of what they measure. That's the idea.
Yes,
They may have.
yeah, if I may, this is quite practical, just to make it clear to our audience. Like, it really has to do with the way you orient your measurement apparatus, like your screen or your detector or something like that, and the fact that you can do it independently from what other people do in another lab. Sorry if I jumped in, but this was...
No, that's perfect.
Then we end up talking about entanglement and locality. It's important to bring things back to the ground, right? This is really practical.
It is. And the notion of locality doesn't mean, oh, there are some things that are common to both labs or some things that can be permeating from one lab to another. Yes, but we assume that at the very least, the decision about the setting, so if it's a Stenger lag, how I decide to orient the setting last minute can depend on me and only me and not on what they decide there.
Yes.
That's the notion of locality. And of course, if you also believe this is the most fundamental notion, if you believe in relativity, then you would say, well, relativity imposes a limit on locality in the sense that I cannot do anything here that can influence there until you wait enough time for light to propagate. Oh, sorry, until you wait enough time from light to propagate from one place to another, right? Again, the notion of locality is more fundamental. You don't need relativity for locality. It's a very common sense notion, if we want, which is two labs can make decisions independently to the local experiments, right? And the relativity actually imposes as a decree. Relativity says, aha, in fact, if you're doing something fast enough that there's no time for light to propagate from A to B until they make their decision, that's imposed locality. So relativity has locality baked in, a notion of locality, a particular notion of locality. Now, something that is interesting about entanglement, and that's the one thing, one of those first experiments, if you want, that manifest true quantum nature, something very different from classical expectations, is what was called the Bell experiment. The notion of entanglement bothered Einstein and many colleagues, and Podolsky and Rosen wrote a paper, but not only. There were people who have a more relativistic background were very bothered by the notion of entanglement. And there were these discussions with people like, with Bohr, with Schrödinger, about collapse, in particular in the context of entanglement. We said, like, this notion of, oh, I act on A, am I affecting B when I act on A? Those discussions, for a long time, the philosophers of physics, and physicists above all, consider them to be of philosophical nature, kind of metaphysical, in the sense, well, in practice, doesn't make a difference if quantum mechanics is fundamental or not, and if there's a problem here or not. In practice, we have things that work. It was until
somehow.
That's right. Shut up and calculate. That is, which I hate madly. But shut up and calculate is a philosopher. So it was actually a philosopher of physics, as Bell in particular, who actually came up with a proposal of an experiment that can actually contrast those notions and actually falsify, which is fantastic. Things go from metaphysics to physics the moment that you are talking about falsifiable things. And that's fantastic. So the theoretical experiment is the following. So Bell makes no assumptions about the theory that underlies nature. He says, well, let me consider a very generic theory underlying nature. And I'm going to impose two things on that theory, and only two things. I'm going to impose that the theory is local and that is realistic. So let me explain the meaning of those words. Locality means what we talked about, meaning that I have two labs, they're doing experiments, they can be measuring a physical system that has two parts. Maybe somebody generated a pair of particles or whatever. They send one to lab A, one to lab B. They're doing whatever they want. They are able, or whatever kind of experiment you can think, but the labs are able to make their decisions independently. That is the assumption of locality. And then there is also the assumption of realism. The assumption of realism tells you that, well, your theory may be probabilistic in nature, but that probabilistic in nature that you have, it's coming, the probabilistic nature that you have, it's coming from an underlying theory that you don't know about, that may be more fundamental than the one you have, that itself can be probabilistic, but in the classical sense even. So a theory where, similar to the balls, just for, again, a little bit inaccurate, but just to relate it to things we said before, there are colors for the balls, and there are variables that have a definite value, or at least a classical probability distribution of values, and those and the values of those affect and determine your experiment as well. That's the notion of realism. You could have none, you could have one, you can have infinitely many. I don't care. You're just saying that, when Bell proposed it is very foundational, very fundamental, very general. You assume with just these two things, locality and realism, meaning that if you don't know something, it's because there's hidden variables, he called them. There are some variables that can be common to both labs, actually, that, maybe you have an ether or whatever you want permeating both labs. And those variables contain information about the experiment that you need to explain the experiment. It's just saying that only the outcomes of the theory and the settings is not enough. You need hidden variables, right? Now, with these two assumptions that are extremely general, the assumption of locality and realism, and the name is very good because it's saying, as we were saying with the balls for real, they have a color. The color of the ball is a real property that is definite in a way. Yeah? So this realism and locality alone, he finds that, for example, measuring observables that can have value 1 and 0, I'm not going to get into the particulars, there's a particular combination that you can build out of the experimental data that in particular, the particular case for binary outcomes will always be less or equal than 2. There's no way to get a value larger than 2 with correlation functions of these experiments built in a particular way. There's just no way. Either the theory is non-local or non-realistic or none, then you cannot violate that.
Yes.
And then the next step is, okay, what does quantum mechanics predict? Now we know in general for any theory that if it's local realistic, you will not be able to measure these correlators to have a value larger than 2. What about quantum mechanics? And with the math first, with the math of quantum mechanics, you say, okay, if quantum mechanics behaves according to the math, then we find that you can violate that inequality. That's called Bell inequality. You can obtain a value measuring the things that Bell said. You can obtain a value that is larger than 2. In fact, it could be as large as 2 times root 2. And that means mathematically that the theory, we're not talking nature yet, but at least the theory of quantum mechanics, it's either non-local, non-realistic, or none. Because those are the only two assumptions that went into building this limitation of value 2 for these outcomes, right? And then you can say, okay, maybe our model of quantum mechanics is wrong. Can we go to an experiment and do it and actually show if nature, regardless if it's quantum mechanics or not, does nature violate those inequalities? Because then if they do, it means that nature is either non-local, non-realistic, or neither. And then experiments, and it was in the 80s, the first experiment was a Lana Specht in the 80s, right? And then later on refining, because there were still controversial loopholes, if you want, as to like, is that experiment satisfactory or not? I think nowadays, very few people would argue that there are loopholes. We have experimentally proven that nature violates Bell inequalities. So whatever the theory of nature is, and actually it does in the way that quantum mechanics does, but whatever nature is, whether you believe or not in quantum mechanics, nature is non-local realistic. Now, this has led people often to say that is non-locality. Quantum mechanics has non-locality because, again, this violation of local realism. Once in fact, quantum mechanics, certainly QFT, is by construction local. QFT is a theory that is by construction local, and it's quantum as well. And you can have entanglement, and of course, QFT. Oh, sorry. Go ahead.
No, I just wanted to somehow repeat what you said, because this is important and I think often misunderstood. These experiments by themselves have nothing to do with quantum mechanics or quantum field theory. That's the crucial thing. They just have to do with nature. So whatever fundamental theory you have, it will either have to be non-local or non-realistic, meaning that things do not have definite properties before you measure them, or both.
Or neither.
Yeah, neither. I don't really know how to imagine that, but please go on. I just had to make this super clear because it's crazy, and I think that even in the way the Nobel Prize a couple of years ago for these experiments was communicated, kind of overlooked this aspect in a way, like it was not delivered properly in press and in science communication in general. So this has to be made very clear. So whatever, you have to sacrifice at least one of those.
Correct. And you see the one thing, I agree with you that it was not communicated properly in that regard. That is not about quantum mechanics, it's nature indeed. It so happens that quantum mechanics seems to be very good at actually predicting what nature does. But regardless, even if quantum mechanics turns out not to be correct, the world will still be either non-local or non-realistic or neither. And the other thing that bothers me, and that's the personal, being a person working in QFT, the use of non-locality for quantum mechanics does bother me. Because QFT, for example, you can build models of quantum mechanics that are non-local if you want. Collapse models, actually. People working on collapse models do that often. But you can certainly work with quantum field theory, which is a local theory by construction. This is not controversial, mathematically local. And you can have all these things that you have with entanglement. You can violate Bell inequalities. And indeed, what fails, what I would say the important feature that fails is realism, that there is no such thing as local hidden variables. That this assumption that, no, that here there's other things that you don't know, the probabilistic nature of nature or of quantum mechanics, depending which one you talk about, comes from ignorance of other things that we just don't know. The theory is not fundamental, we just ignore things. That is the thing that's not true. That's the thing that, of course, it may be the case, maybe when we learn how to do quantum gravity, maybe I have to correct myself. In fact, locality may fail in quantum gravity, no problem. I have no problems with that at those levels. But at the very least, in anything that we can see in our labs, the locality is sacred, as sacred as relativity in a way. And to me, what fails is locality. So when people, well, sorry, realism. So when people call quantum mechanics non-local, I feel bad. I feel a little bit of pain inside because I don't think quantum mechanics can or cannot be non-local, depending how you build some parts of it. But certainly, the way of doing quantum mechanics that is the most fundamental way that we know of doing it is local by construction.
Yeah, you can
And
come up with, that's important, you can come up with alternative theories that sacrifice
yeah,
locality to reproduce quantum mechanics. You have like bombs, pilot wave, all these things and all
precisely,
that. But things get much harder when you want to include special relativity and replicate quantum field theory, right? Because their
precisely.
locality is baked into the theory. That's important. Like you do not only have to replicate the experimental predictions of quantum mechanics, but really of quantum field theory. That's the hard task.
That's precisely right. Quantum field theory was developed precisely because there were things that with regular quantum, non-relativistic quantum mechanics, you cannot explain. And you need, and there are things that are not very contrived. You don't need to go to high energy physics. Things like the lamp shift in atoms to explain atomic spectra. You need QFT. You need to have a relativistic formulation of quantum mechanics. And things that you observe every day, like matter and antimatter, so positron electron pairs production. You need a theory that is at the same time quantum and relativistic, in order to predict many things that we see and use in technology, right? So
Even particle creation, in a way, in
yeah,
general,
yeah,
right?
exactly.
I have a light here, light in my face, and there photons are produced, right?
Well, I would be
You
so another thing that I try
you
to be
can
careful is with the
force.
photons thing because it could be a bit misleading. There is so the notion of photon is kind of funny. There's an article by Lamb, but I talk about the Lamb shift. But there's an article that I encourage people to read the abstract. It's a very outrageous abstract. So maybe if you want to overlay it or
Wow,
something, it's perfect. The article is called
I will.
Anti-Photon. The article is called, maybe I can even, can I share screen just to read it with you?
Ah, absolutely, absolutely. Let's
Okay,
do
okay.
that. Let's break the
Okay, photon
rules.
lamp,
Sure.
because it really deals to the core of why measurements are difficult too in many ways. So let me the article is, I would say, less interesting than the abstract. It is interesting, of course. Oh, open system setting. I need to allow.
Ah, gosh, gosh.
So maybe it's not possible, right? I
But
don't
if
know.
you want to read it, I'll overlay. There's no problem.
Perfect. I will read it. I will read it then. I will do it later because I need to close Chrome for this. Okay. Let me just read it. So it should be apparent from the article is actually called Anti-Photon. Okay. So that gives you already an idea. And it says, it should be apparent from the title of this article that the author does not like the use of the word photon, which dates from 1926. In his view, there is no such thing as a photon. It gets more spicy. Only a comedy of errors and historical accidents led to its popularity among physicists and optical scientists. I admit that the word is short and convenient. Its use is also habit forming. Similarly, one might find it convenient to speak of the ether or vacuum to stand for empty space, even if no such thing existed. There are very good substitute words for photon, e.g., radiation or light, and for photonics, e.g., optics, or even better, quantum optics. Similar objections are possible to the use of the word phonon, which dates from 1932. Here's the key. Objects like electrons, neutrinos of finite rest mass, or helium atoms can, under suitable conditions, be considered to be particles, since their theories then have viable non-relativistic and non-quantum limits. Then the rest of it is this paper outlines the main features. So it's a bit funny to do it. It's a bit radical in the way they speak. Let me tell you, I use the word photon like most physicists do, but one has to be really careful because when one really wants to define the notion of photon, it becomes extremely difficult. For example, we tend to say, so I think in school, people would tell you photons are the quanta of electromagnetic radiation. It comes in packets of energy. And they use the photoelectric effect for that. That is very misleading because they typically say, oh, you see, if I increase the intensity of light, I'm sending more photons. But if each individual photon doesn't have the energy to take an electron out of the atom, then it won't happen. Then it's proving the existence of photons. That is not true. You could have, you need something quantum for the photoelectric effect, but it doesn't need to be light. It can be matter. If you have quantum matter, you get exactly the same threshold effect. And if you say, okay, what is a photon? People will tell you, well, it's something localized in space. Well, a state of light localized in space. I can make you a classical. I can get a flashlight and shine, and that's nothing. There's nothing quantum about it. And what about the way energy comes in packets? Well, energy can come in packets in classical systems as well. I have an optical cavity with mirrors looking at each other, and there's only a certain discrete number of wavelengths that are allowed in that cavity. You can only excite the cavity in discrete ways. Okay, how about the opposite? Can I have a quantum object whose energy is not discrete? Of course, you can have a free electron, for example, that can have any energy you want. It's not coming in discrete packets, right? So when we talk about photons in physics, we mean something called a Fock state, which is something like a single particle excitation of the electromagnetic field. Those things don't behave anything like classical particles. If you have a mass, yes, if your field has a mass, you can get one of those excitations, move to the reference frame that the particle that you created, the excitation, is at rest, and it pretty much looks like a quantum mechanical particle that in many ways looks like a classical one, only that the classical particle has a definite position and a definite momentum. It's localized in space and in speed, if you want. The quantum one, we say, no, it cannot be localized in both, but you know, you can you can have decent localization in both, at least for a while, and that we call a particle. In QFT, when you create a massive excitation of a field like that, yeah, okay, you can move to the rest frame of the excitation if you want and have something similar, in fact, reproduce very well a quantum mechanical particle. But if your field is both quantum and massless, you have a problem. Those Fock states that you're creating are either not much like particles, or they live everywhere and existed for all times. And if you want to localize them, then it may cost you infinite energy to actually localize them. And indeed, what you localize has to be something that is not a particle. It's more than a Fock excitation. So what we do in the lab that we call single photons are not quite single photons. They may be very approximately single photons, but if it fits in your lab in the time of your life as an experimentalist, it cannot be a photon in that sense, in the purest sense, right? So one has to be careful. I always am very careful with the notion of particle, right? In that sense.
So I'll pretend to have used the word photon on purpose to prompt this interesting explanation, which might have allowed the audience not only to grasp at how precise you have to be when you work with these kind of theories, but also at how complicated things get even when you work with such a simple thing as the electromagnetic field, which is arguably the simplest of the fields we work with. And this gives way for another question, which kind of goes to the core of our conversation. Namely, if things get this weird with the electromagnetic field, what happens when you go to gravity?
Right. So the short answer is we don't know. And then there's a longer answer because we've been many years trying to, by we, I mean, not me, I mean everybody in physics and doing these kinds of physics, trying to understand gravity. There is a very nice XKCD comic, right, that I'm gonna quote here because it really illustrates a little bit the thing. It's a teacher, a professor or a teacher, I don't know, explaining to younger people what are the four fundamental interactions, no? And then it says, well, we have gravity. Gravity is the one, is the interaction that keeps us bound to Earth. You experience it every day when you drop things. It's what keeps the Earth going around the sun, the galaxy together, etc. Then, and the kids say, okay, yeah, makes sense. Then they say, well, then we have the electromagnetic interaction, which is, you're associated with magnetic fields that you've seen in magnets and charges. I'm paraphrasing, and not literally the same as the comic. With magnets and it's also when we study the atom, there's a charge distribution outside the atom is what prevents you from going through objects as well and keeps you firm on the ground and so on, and say, okay, it's a bit weirder, but all right. And then we have the strong interaction. The strong interaction keeps the atomic nuclei together. and it's also keeps your protons and neutrons as stable systems. I say, what? Sorry, I'm not sure I understand that one. And there's the weak interaction that is responsible for radioactive decay. Says, and then it's like, what? No, no, hold on. What do you mean? And then the next thing, of these four interactions, there's one that we don't understand at all. And then the kid asks, oh, it's the strong or the weak one? And no, it's gravity. So this is where we are. It's literally the most difficult fundamental theory to understand. And while we have done very well, I think we have a very good grasp on not very strong gravity. And don't get me wrong, not very strong gravity can mean very close to very dense objects like black holes. We do understand what happens pretty much. This is an intuitive. The bigger the black hole, the easier to understand because the stronger the gravity is when you get to the horizon. You can understand almost close to all the way, very, very close to an event horizon of a black hole. So far, general relativity and what we know of quantum mechanics can explain things that we see. We haven't seen yet any astrophysical phenomenon that has not fit, with an asterisk as usual, but generally that has not fit with the theories that we already know. Because we haven't really seen strong gravity, or what we call really, really strong gravity, to the point that you need something beyond general relativity and quantum field theory. Now, it so happens our best quantum theory so far, without talking about quantum gravity, the best uncontroversial quantum theory that we have, which is QFT, still relies on the causal structure that general relativity overlays in it. So in a way, QFT requires that there's a space-time background, and that space-time background that works like either like relativity, or you can modify relativity the same way, adding corrections to relativity, but still some sort of classical background, not quantum background. And we know that this way of doing things is not good enough. It's kind of super interesting because unlike other theories in the past that you actually needed experimental evidence to do something weird and new, quantum mechanics would not have been started by Planck if we didn't face problems like the black body radiation ultraviolet problem or the stability of the hydrogen atom, because it's very weird. Who would want to do quantum mechanics? It's very weird, very complicated. We only did it because experiments pushed us. We needed it in order to explain what we see. And like that, right now we know, even from the theoretical physics point of view, general relativity alone predicts monsters that cannot be compatible with the theory itself. So if you go to super strong gravity in general relativity has issues. Inside a black hole, inside an astrophysical, or what we believe an astrophysical black hole to be, we have issues. You don't need to even go to singularities or rings of singularities. You get crazy things like like mass horizons. You get closed time-like curves. You get things that are not compatible with what we believe a physical theory should be, which is a predictable thing. So we know general relativity has to break down. And yet, so far, we have no alternative for it that one consensus, let's say, alternative for it. People have been trying to do many different approaches to trying to do a quantum theory that also people have also gone other ways, and not only quantum theory, but that's more marginal. Let's say that the standard ways, like people trying to find, not to say they're not good, people like Jonathan Oppenheim does incredible cool things with stochastic gravity that are extremely serious, and I'm excited to explore as well. But in quantum gravity, what people try to do is treat the same way, or at least in a similar way we treat everything else, treat gravity, and that comes with its own set of problems. In particular, the structure of spacetime itself not being able to be assumed, but something emergent, makes it extremely complicated. And so far, there's no consensus successful way of doing this.
So if I may, first, our previous interview was with Andrea Russo, a PhD student in Jonathan Oppenheim's group, so it really fits.
Yeah, nice.
This sounds like something we prepared, but we didn't actually.
Perfect.
He's going to that after having seen this. And secondly, we are on the YouTube channel of the International Society for Quantum Gravity, and we would need no International Society for Quantum Gravity if we had solved quantum gravity, right?
That's
so
right.
the problem is somehow, at least partially, I would say largely still open. And there's a variety of approaches to it.
That doesn't mean there are not a lot of. Oh, sorry. Go ahead.
No. It's really important to stress that people discovered things, understood things. There's steps we do, but we still haven't reached like a satisfying answer. And in that sense, one thing you mentioned is really important, namely the fact that we cannot really probe strong gravity, right? It's really hard to come up with experiments that allow us to explore quantum gravity. But there's a thing you mentioned before, which is entanglement, and you somehow briefly touched on the ways in which entanglement might connect to the issue of quantum gravity. And this might even lead us to, you know, some thinkable experiments, something like that. But first, can you tell us something about the ways in which entanglement factors into the problem of quantum gravity?
All right. So this connects. So let me give a segue to it by talking about a tiny amount about measurements too. So the interesting thing, right, is that, or at least this is a little bit of my bias because that's kind of my research as well. Measuring in measuring, even if the systems you're not measuring are not gravitational, the fact that if you are able to describe measurements, again, this is entering into things that I'm interested in, rather than be mainstream, but I will connect it with mainstream in a second. If the very same measurement is modeled as a quantum measurement, and again, we talk about clocks and rulers that are quantum, then the notion of quantum gravity may emerge from that already. So if you try to do the same thing that Einstein did with rulers and clocks, but now your rulers and clocks are quantum, and you don't assume that there's a background causal structure, but rather that it emerges from the quantum measurements, right? Then it might be possible. So that's a scenario in which it might be possible to relate something very, very quantum, which is the nature of the measurement problem in quantum mechanics, with the quantum nature of gravity. Maybe that would be a way of talking about an emergent gravity out of quantum degrees of freedom that are related to our way in which parts of the universe interact with each other, no, and get entangled with each other. But let's go to the experiments, no, because the actual realistic experiments that have been proposed, because it's something that is very trendy right now and very exciting, indeed, which is well, people started to look at okay, what happens in a context in which we have two systems that are originally not entangled, but they may be able to get entangled through interaction. We know that it's very easy to actually get, it's easier than people think to get entangled. In a controlled way, not as much, but if you don't care what kind of entanglement, just touching something is entangling you without something. Most interactions entangle. And in particular, the gravitational interaction entangles things, entangles quantum systems. So the question, the very interesting question is that, okay, imagine that we do an experiment in which we observe quantum systems getting entangled only through gravitational interaction. Can we use this, or at least some form of this, to learn something about the quantum nature of gravity? And this is based on the fact that it is known. So this is the theoretical work that has been done on, okay, if A and B are interacting with a system C, whatever it is, could be classical or quantum, but the interaction is local, well, then if the interaction is local, so A only interacts with C over here in a way, then C carries the interaction to B and they interact locally like that, then C has to be quantum in some way. So C is establishing a quantum channel between A and B, and a classical medium cannot support a quantum channel. Maybe this is proof that gravity is quantum. That's very exciting. Those are the family of experiments known as gravity-induced entanglement experiments. Now, of course, I have to say that one has to be careful. This is very exciting. One has to be careful because, so first of all, if we observe that, if we have something like what is known as the VMV experiment, that is, you have some, let's say, atoms, if you want. You prepare an atom in a superposition of being in two positions at the same time, and another atom in a superposition of being in two positions at the same time. And you let them evolve interacting with each other only through gravity. They eventually become entangled through gravity. If in the far future, by far future I mean seconds afterwards, you measure the atoms and you find them entangled, then, or you violate bare inequalities with them, whatever you want to do, then what have we learned about gravity? And this also connects with things that I'm very interested in. So one thing you learn is something that we already expect, but this is not big surprise, but it's experimental confirmation of, which is that what we call semi-classical gravity doesn't work. Semi-classical gravity is basically get general relativity, the main equations of general relativity, Einstein equations. On the right-hand side, you have matter. On the left-hand side, you have gravity. Semi-classical gravity is saying, well, matter can be quantum. Of course, I cannot put the right-hand side of an equation in a form of a quantum system without the left being in a quantum system as well. I don't know how to do quantum gravity. Let's just take expectation values on the right. Let's put the quantum thing. Let's average in order to drive the classical equations of gravity. That already would be falsified because that cannot generate entanglement between the masses. So that would be experimentally falsified. Now, on the flip side, nobody expected semi-classical gravity to be a fundamental theory. It's an effective theory, like many others, that works very well within the regimes it works. Nobody thought that we are this is a valid candidate to explain how gravity works. But then again, that doesn't subtract from the fact that we will immediately see an experimental falsification of it. It would be the first tabletop experiment doing it. The question is now whether we can learn many more things. And we do. In fact, we do. But we need to be really careful, and I would factor that in, really careful on what regimes you can learn things from it or not. For example, this is where things like what Jonathan Oppenheim is doing, or what I've done as well in some of the work, is, well, there might be some theory for gravity that is not a quantum theory for gravity, that's still able to explain the outcome of getting the two systems entangled without meaning that gravity is quantum in the way we think is quantum. So we know that you will need to violate, for example, things like locality to do it. But if you violate locality in ways that are allowed, so for example, even quantum gravity itself will probably violate relativistic locality, right? If relativity is no longer valid as some regime, you would not expect the notion of locality coming from it to be valid in the regime, perhaps. So I don't have that much problem allowing for non-locality at the fundamental level of quantum gravity. But you see, to really prove that it's a quantum field theory similar or something similar to what we have is not enough. You may have a non-quantum theory, and it's not quantum in the sense that it can still be ill-defined. It could be probabilistic. It cannot have a definite value at a point, but yet not be what we would call in physics or in theoretical physics quantum, which is something that has gone to the quantization map, some quantum degrees of freedom, some algebras observable, self-adjoint, all what it means to be quantum that comes with all the. So that is something that tabletop experiments can still probe, but one needs to be really careful. Like, for example, you can try to get them entangled while in space-like separation. That sounds wild, but you can actually do it. That's called entanglement harvesting. I told you that quantum fields have entanglement everywhere. So you can actually get the systems entangled through extracting entanglement from the field. That certainly proves that the field had entanglement, and entanglement has that in nature. Simpler than that, you can do the experiment in times that are less than the return light time from the two. That's a proposal that came from Wald and Flaminia Giacomini and others. That indeed that would be incompatible as well. From it would be a case in which you should be able to see, because you would have retrocausation in your theory otherwise if you do it classically. So there are extreme, let's put it like that, extreme regimes, not as easy to reach in the lab as just waiting for a long time and let them get entangled. But this has to be paid attention to. So there are regimes, if you really want to make a claim that a tabletop experiment is telling you that there's an underlying quantum theory for gravity with no controversy about it, you need to be careful within what regimes you're measuring. Not saying that the experiment as proposed, the long time one, would not be important. It would be extremely important. But I think one has to be careful with what are the assumptions that one makes in order to claim that the field is quantum. Yeah.
That's tremendously interesting. Yeah, it's important to be careful. Nonetheless, at least seeing a glimpse of light, right, at the end of the tunnel, the possibility of starting to probe this and learning something.
I can also say, if you don't mind, sorry for interrupting, but I think this is important to also emphasize that, and like maybe like 15 years ago, we thought that there would be no testbed for quantum gravity other than perhaps cosmology, you know? Like you need like tremendous early universe level of energies to do it. The fact that we are thinking now of tabletop experiments that may not be able to be done now, but maybe in some decades, that can't even probe quantum gravity at all, this is revolutionary. And that shouldn't be, I want to emphasize that, despite the fact that I tend to be conservative in what the claims should be done. I try to be careful with those, exactly what you need to assume to make the predictions. This is revolutionary. Like thinking that you asked me, but again, I didn't know much 15 years ago. But I can tell you, if you ask me before knowing about gravity-induced entanglement, if I expected to see an experiment at tabletop scales that can probe quantum gravity, my first answer would have been, there's no way. Look where we are. So, yeah.
And I guess since you brought yourself, like your past self, up in this retrocausal fashion, I guess this might be time for me to ask you a final, more personal question. Like, and thank you for all the time you spent with me today, which is, let me frame it like this. Why did you decide to do this? Like, why did you decide to get into physics, into this kind of physics? What excites you about it? This can be extremely helpful for our audience, young people maybe deciding what to do with their life.
Okay, I always when I answer questions like this, I always give the warning that every person is very different. So what works for some people may not work for most. But
That's why we
certainly,
collect many, right?
yes,
We
yes,
collect
I was
many.
about to say, being exposed to many people. In my case, so when I was since I was a kid, I was extremely curious. I always ask questions, right? And sometimes the questions had answers. Sometimes people would not be able to tell me the answer. So I thought, uh, okay, when it was time to choose what to do, I found myself, well, I'm good at math. I like science. Um, I think that this is one of the ways I can get answers. Also philosophy, like I consider philosophy too. Like I want the most answers. I want the path of life that would give me the most answers. And I decided to do physics. I was wrong though, because again, physics doesn't give you the most answers; it gives you the most questions. But that's okay, because then I found out that
Trick.
the the useful learning actually happens when you ask the right questions, right? The questions that are not that easy to answer. So it gives you answers, but it gives you more questions than answers, and that's not bad. So if in my case, is sheer curiosity and trying to understand how things work. And if people want to understand how things work, right, I think physics is not a bad path to take. Let me say, not the only one, but it's certainly not a bad path to take. And in particular, I decided to go foundational, as foundational as I thought I could be, looking at quantum field theory, looking at quantum theory and relativity, and of course that quickly also very interested in quantum information. I also, when I was an undergrad, it was a time that quantum information had a huge push and revolution, because technologically people saw that you can build these things and you can do crazy things with them. So quantum information inspired me a lot. So I also tried to combine this fundamental reach of okay, where do we come from, where are we going, what are these things that we see and experience, together with quantum information. Turns out it was a good bet, because quantum information has a lot of tools that are very useful to try to understand at the fundamental level what's going on with the structure of space-time. So all these things together is what pushed me to do what I do. My path was like something called relativistic quantum information that tries to, it's an interesting field, it gets people from everywhere, different backgrounds, to converge and talk about these things together in the common sharing of quantum information theory, I guess. And this is what inspired me to. I don't know if that's helpful, but at least that's definitely what the way I went.
It is, it is. And with that, I would thank you again for your time today. And I would
Thank you
also
very
thank our audience. I would also thank our audience for having stayed with us for 1 hour and a half.
Thank you, and thank you for the interview. I want to thank you in particular for your interventions. I think were extremely helpful as well. So I'm very happy.
Too
Yeah.
kind, too kind. Thank you again, and see you soon.
See you soon.